Hello, friends. Once again, I welcome you all for my lecture number 4 on scattering theory. You know that in lecture number 3, we have studied the plane waves and we have expanded plane wave as a linear combination of a spherical wave. So, a plane wave is thus an equivalent to the superposition of an infinite number of spherical waves. And in the previous lecture, we have found if a particle is moving along z-axis, is a free particle, it can be treated as a plane wave. And we have represented this plane wave as e to the power of ikz. And we found that this plane wave can be expanded as a linear combination of the spherical wave. So this equation number 1, which we have established in previous lecture, this formula is known as a Boyer's formula. So we will use this formula for many numerical problems for the scattering theory. So please remember this expression. This is the Boyer's expression, that is the plane wave expression, which is treated as a linear combination of infinite number of spherical waves. Here you know that GL of KR is basically a spherical Bessel function of order L, and PL cos theta is a Legendre polynomial. So the each term on the right hand side of this equation number 1 is representing the spherical wave. And you see the plane wave is an equivalent, the superposition of infinite number of spherical waves, and each individual wave, which we have mentioned in equation number 1, each individual wave is called the partial wave. So these waves are characterized by the quantum number L. So you see the waves with the quantum number L is equal to 0, 1, 2 are respectively called S wave. So if you have a spherical wave which is considered as an S wave, for that S wave we have L is equal to 0. So if you want to write the expression for the S wave, it will be L equal to 0. So it will be I to the power of 0 2L plus 1, that is equal to, that is L is equal to 0. So you have J0 of KR P0 cos theta. That is the expression for the S wave. You can have expression of P wave. You can put L is equal to 1 as L equal to 2, and you can have the S partial wave, P partial wave, P partial wave. So now you please understand that we would like to study our expression, and we want to study the asymptotic behavior. So here I wrote the spherical Bessel function, which is JL of rho, that is a spherical Bessel function of order L, can be expressed as 1 upon rho sine of rho minus L pi by 2 when rho is very large, that is rho is infinite. You please remember these expressions. Similarly, you can see here that I wrote here asymptotically JL of KR is equal to, this is rho. Now the argument rho is replaced by KR. So we can write JL of KR is 1 upon KR sine of KR minus L pi by 2. So this is, we have to remember this expression for when rho is very large, when we study the asymptotic behavior. So now you can see that the plane wave expression, this expression number 1, we will rewrite this expression e to the power of ikz, that is the left hand side, this is the plane wave expression, is equal to I to the power of L. I write I to the power of as it is. 2L plus 1 we will write as it is, but this JL of KR we will write down its asymptotic behavior JL of KR. So which we will substitute JL of KR in this expression. Just a minute. So let's see. Here I write down this JL of KR in this expression number 1. So you can see here uh, this expression, this is just expression number 1, it is I to the power of L, 2L plus 1 is remaining same, and this is JL of KR. And so JL of KR, I substitute JL of KR here, that is equal to 1 upon KR sine KR L pi by 2, and this is PL of cos theta. Okay, so this is now this step you can understand. Simply you look at your equation number 1 here. This equation number 1 here, I substitute GL of KR is the asymptotic behavior at a large distance. I calculated when R is very large. That means when a particle is very far from this scatterer, right? So that is where R is very large. So in that case, I substitute the value of GL of KR here, and I modified this equation, and this is the equation which I am getting. Now I can rearrange. You see, I to the power of L is remaining as 2L plus 1. So I am writing 2L plus 1. 1 upon KR, I am writing 1 upon KR. This is, and this PL cos theta, I can write it here. And now you know the sine of theta. This is theta, where theta is KR minus L pi by 2. You have studied sine of theta is always e to the power of I theta minus e to the power of minus I theta divided by 2i. So using this expression, I can write now this sine theta. So here theta is simply kr minus L pi by 2. So you can use this expression. So you can see this as e to the power, that is exponential I kr minus L pi by 2. There is a minus sign. So again there is a minus sign, exponential of, so this is exponential of minus I theta. So minus I theta is this is your theta kr minus L pi by 2. So I write here minus I, and divided by 2i, so this is divided by 2i. Look at this expression. Now let us try to interpret this expression. So this expression, you see this term is exponential of e to the power of plus ikr minus il pi by 2. The other term is exponential of minus ikr plus il pi by 2. So what we can say, and this equation shows that each partial wave can be represented as the sum of incoming and outgoing spherical wave. So each partial wave can be represented as the sum of incoming, right? As incoming, that is e to the power plus ikr, and outgoing spherical wave. That you can see this is the term minus e to the power minus ikr plus L pi by 2. Our basic problem is that today we want to study the partial wave analysis. So before we study the partial wave analysis, let us see some interpretation of this equation. See, in scattering problem, the first few spherical waves are very important. That means when you study the scattering, you see here, look at the diagram, which you will realize. This is basically a beam of incident particle which is moving along the z-axis. These are free particles, so it is treated as the plane wave. So this is the plane wave which is moving along the z direction, which we written e to the power of ikz. And now when they enters, when this plane wave enters in the potential field produced by the target particle, there is a interaction between the incident particle and the target particle. and you have a process of scattering takes place, and because of the scattering you have the scattered wave. You can see this, these are the scattered, the spherical waves which we have discussed, right? This scattered wave is a spherical wave which we have represented, which is moving radially outward direction, which is represented by e to the power of ikr. So e to the power of ikz is the incident plane wave, and you have e to the power of ikr is basically a scattered wave, right, which is moving radially outward direction. So this scattered wave, the first, you see these scattered waves are different scattered wave. You have the S wave, you have the P wave, you have the D waves. So these waves we would like to understand, and that is why I said that uh, first few waves, that is the S wave, P wave, D waves are very important in scattering theory. So we are interested to study the spherically scattered wave. The spherically scattered waves are characterized by S wave corresponding to L equal to 0, P wave corresponding to L is equal to 1, D wave corresponding to L is equal to 2. So these waves we would like to understand. We want to we want to see the characteristic of this scattered wave, and that is why you see these S partial wave are very important, because the S partial waves are independent of angle theta, and hence they are spherically symmetric about the origin. These waves are very useful to understand the low energy scattering. So please remember, the results of extremely low energy scattering can be explained satisfactorily with the S wave only. So if you have your incident particle which is moving along z direction, and if the energy of the incident particle is low, and if you want to understand the low energy scattering, if you study the S wave scattering, then you will get the clear picture about the scattering for low energy scattering. And to see if the energy is sufficiently high, then one needs P waves scatter. You have to study the needs of P waves to understand. So we have a linear combination of many spherical waves, right? And we want to study the each spherical wave. So first spherical waves for corresponding to L equal to 0 is known as the S wave. S waves are basically used to understand low energy scattering. We have a P wave, so we would like to study the partial wave analysis, and we will study the physics of S wave, P wave, and D wave in our next topic. So, once again, let me summarize that you have a plane wave. This plane wave is basically treated as is a linear combination of infinite number of spherical waves. Each each spherical wave is considered as a partial waves. There are many partial waves. We have a S wave, which is characterized by its quantum number, orbital quantum number L equal to 0. We have a P wave, which is characterized by its orbital quantum number L is equal to 1. And you have to find out the analysis of the scattering analysis of S wave, a P wave, and the D wave to understand the energy to low energy scattering as well as the high energy scattering. So now we will try to understand the partial wave analysis, and once you want to study the partial wave analysis you have to study the scattering, and when you have a scattering, then scattering is because of some potential. So we consider a central potential. So basically, we have the scattering theory. We have a system of two particles, right? And the relative distance is changing as particle is moving along the z direction. So we have a target particle or a group, a target particle or a group of particles which is located at the origin of the coordinate system, which is kept at on the z-axis. That is the origin, right? Which we have already discussed. And please remember that we can use a Schrodinger wave equation to understand the partial wave analysis. Here I have considered the central potential. That means there is a potential which only depends upon the relative distance r between the two interacting particles. So this is the potential which is only r dependent. That is, it is depending upon the relative distance between the two interacting particles of the center of mass system. So friends, now let us consider a Schrodinger equation which I am writing a time independent equation, del square psi plus 2 mu over h cross square e minus v of r psi of r is equal to 0, which we have considered for a system of two particles because we want to study the scattering theory. So we have a incident particle and we have a target which is stationary, which is kept at the origin on the z-axis, right? Because that you have studied. Now you see here the potential V, this potential V is only depending upon the relative distance r between the two particles in the center of mass system. So there is the force is acting between the two particles which is joining the center of two particles, I would say. You have a central potential, so the two particles are interacting, so there is a force acting, and this force is acting is along the line which is joining the center of two particles. I would say that this potential is only depending upon the distance, relative distance r between the two particles. So you see here, here I have mentioned as the incident particles are along the z-axis, the wave function psi is to be independent of phi because particles are moving parallel to z-axis. And using the method of separation of variable, we can solve this Schrodinger wave equations. So your psi basically, which is a function of r theta phi, but you see here that since your particle is moving parallel to the z-axis, along the z-axis, your wave function psi is independent of phi, which I have already explained in my previous classes. So I use the method of, I want to solve this equation because I have a system of two particles and I want to solve this Schrodinger equation for a system of two particles where mu is the reduced mass of a system of two particles which you have studied. So here you can see I can write my now wave function because it is a function of r and theta, it is independent of phi. So I can write psi, which is a function of an r and theta. I split my wave function into the two parts. This is my radial part and this is the angular part. So radial part of the wave function is RL of r, right? And this is your PL cos theta. This is your legendary polynomial of degree L, that is L equal to 0, L equal to 1, L equal to 2, you can write this. And your argument of the polynomial is cos theta, where we can write x equal to cos theta, that is PL of x. So this is, you know this, which we have already developed at undergraduate level. Now you see this RL of R, this this radial wave function, this radial is satisfying the following radial equation, which we have studied when we have studied the hydrogen atom problem at third year BSc. So this RL of R is satisfying This radial equation, this is the radial equation 1 upon r square d by dr r square, and you know that is the derivative of RL with respect to R, 2 mu E over h cross square minus 2 mu V over h cross square minus L into L plus 1 over R square, RL of R equal to 0. This is the radial equation. This because this RL of R satisfies this radial equation which we have already established at MSc part 1 as well as undergraduate BSc classes also we have developed this. Now you see, let us see, there are two regions when you are discussing the scattering problem. There are the two regions which you can see. This is your, this is the region where a particle, you see, we consider the plane wave which is propagating along that direction. But you see, when particle is very far from this scatterer, this is your scatterer, and when a particle is very far from the scatter and it is moving along the z-axis, this particle does not experience any potential which is produced by the scatterer. So I would say that there is a region here where the potential offered by this target particle is practically zero. There is no potential. You see, so in this region, you see that V of R, the potential is zero. And you see there is a region when particle enters into the potential field of the target particle, the particle experience a force because of the potential produced by the target particles. So here there are two ways you can solve the Schrodinger equations. Here the solutions you can solve Schrodinger equation at a large distance, right? Very large distance. That is as asymptotic. When r is very large, you measure generally distance r from the origin, right? And this is your target. When your plane wave is very far, when there is no potential, v of r is zero, in that case, you can see now the equation which we can write now. So please try to understand this expression. So outside the range of potential, so which way I said that the potential range, this is very important. This is the range of potential. You see that if you consider a sphere of radius r0, right? So this is basically considering the range of potential. But if your particle is outside the range of potential, it does not experience any potential, right? So in that case, V of r is zero. When V of r is zero, so you substitute V of r is equal to zero in that Schrodinger equations, and we can find the solutions of the Schrodinger equations because we have a system of this is the equation. We want to find out psi of r theta. This we want to find the solutions of this equation, that is your eigenfunction. And now we solve this Schrodinger equation in the region where there is no potential. So you see that when V is equal to 0, so I see this term will disappear, you see, because you keep V equal to 0. So outside the range of potential, your Schrodinger is the radial equation is 1 upon r square. And I differentiate this part, look at this, because it is d by dr of r square d by dr of RL. So first I differentiate r square and I'm keeping this constant. And then I'm keeping r square constant and I differentiate d by dr of RL with respect to d with respect to r. So you can see I use a product law here. So this expression, one you can see here, 1 upon r square and keeping 1 upon r square. I first differentiate r square with respect to r, so it is 2r, and I'm keeping this factor constant, d by dr of RL, so it is d by dr of RL. And now I'm keeping r square constant, and I differentiate d by dr of RL with respect to d by dr. So it is the second order differentiation of d square RL by dr square. And you can see this is 2 mu h cross square minus this is 0, and you see this term remain as it is, so I write this term as it is. And now once again you can see this expression. You can solve this, open this when you open this square bracket term. So this is, you see here, you can find out this term. This r square and this r square cancels here. So it gives you d square rl by dr square. This term comes here. And this is 2r upon r square is equal to 2 by r drl by dr. So this is a very straightforward steps which is I have derived from when I open this bracket, and now you can understand. And this is 2 mu e over h cross square minus L into L plus 1 r square. This bracket I am keeping as it is, RL of r. This is the radial part of r equal to 0. And now you can see I substitute 2 mu e over h cross square equal to, say, constant k square. I'm keeping value k square. So this is again, you see d square, this step is remaining as it is. The second step is also remaining as it is. And these 2 mu e over h cross square is replaced by k square minus this. So you have this. So this is basically a second order differential equation. And this equation has two independent solutions. The solutions of these equations are basically the Bessel's functions and Newman functions. So there are two independent solutions. So J RL of R equal to JL of KR. So if you take the solutions of this, the first independent solution will be JL of KR, that is RL is equal to JL of KR. That is a spherical Bessel function of order L. And here I am defining another function, that is NL of KR. So there is another solution, that is RL of R. RL of R is equal to NL of KR, some constant into NL of KR. So you see, if you write the solutions of this equation, there will be one solution, RL equal to A, some constant A into GL of KR. And there is another solutions, RL equal to some constant B into NL of KR. NL of KR is a Newman function. It is known as a Newman function. It is a spherical Newman function, and which you have studied when we have studied a three-dimensional square well potential problem, where we have introduced a Newman function of order L. So we have two independent solutions. So the general solution can be the linear combination of these two independent solutions. So I can write down the general solution here. So general solution RL of KR is, I write some constant. So I write, instead of constant A, I write A prime JL of KR, and I write down plus or minus B dash NL of KR. So here you have a constant A dash, and here we have a constant B dash. So these constant A dash and B dash we will determine when we write the equations. We will see how to find constant A, how to find constant B. So here these constants we will evaluate. And now you see this equation, when you write this equation at a large distance, that is asymptotically, because there is no potential at that in this region, because V of R is 0. So you write down JL of KR when R is very large, that we have discussed, and NL of KR when R is very large. So you see I am writing this formula here. I'm sorry, let us see. So this value I can write down. So you can see this is the R, this is general solution. Now I put the value of JL of KR when R is very large. So JL of KR, which we have already substituted, is equal to JL of rho. JL of rho is 1 upon rho sine rho minus L pi by 2 when rho tends to infinite, right? So now JL of KR, so rho is basically KR. So 1 upon KR sine KR minus L pi by 2. This is the value of JL of KR when R is very large. And this is the value of a spherical Newman function when R is very large, is given by minus 1 upon KR cosine of KR minus L pi by 2. So you can see this expression. So the solutions of the Schrodinger wave equations for a system of two particles is RL of Kr is A dash, because you see 1 upon Kr I'm taking in here in the numerator. So A dash Kr sine Kr minus L pi by 2. This is very simple. Similarly, this is a minus sign and here there is a minus sign, gives you a positive sign V dash divided by Kr cosine of Kr minus L pi by 2. So this is the solution of a Schrodinger equation when V of R is equal to 0. Please remember. So this is the equation, the solutions of the Schrodinger wave equations. Basically, this is an asymptotic behavior, asymptotic solutions, because we consider when R is very large, where there is no potential field due to the scatterer, right? Because of the target. And now our problem is that we have a central potential, the particle which is kept at the origin of the coordinate system is producing the potential surrounding it. So there is a range of potential. If the range of potential is say R0, that if particle is in the range of the potential field produced by the target particle, then in that case Vr is not equal to 0. So in that case we now have to write down the Schrodinger wave equation, you see. So now this equation we have to solve. So you see this equation which we have already mentioned, the first equation. Look at this equation which I will show you now. Uh, This equation we have to solve. 1 upon r square d by dr, r square d by dr of Rl plus 2 mu e over h cross square minus 2 mu v over h cross square minus L into L plus 1 r square. This is the radial equations and we have to solve this radial equation because V of r is not 0. Particle is experiencing a potential produced by the target particle or target particles. So in that case, we have to solve this Schrodinger equation. You see, when V of r is equal to 0, we have solved this equation. Now, but when V of r is not equal to 0, we have to solve this equation, right? In the previous case, when the potential was 0, we have solved this equation. Now in this case, when you solve the Schrodinger equation with the central potential, the equation, the solutions are similar to the solution where the potential was 0. You see, so if you see the potential in that region, so you can write this AL divided by KR sine of KR minus L pi by 2 delta L. And you see that Newman part here, you see the other part, this is because of the Newman function. You see, this is because of the basal part, and this is the Newman part. So if you see the solutions of the Schrodinger wave equation, the Newman part disappears because please remember the Newman function when r tends to 0 is infinite. So I give you an exercise. Write down a Newman function, a spherical Newman function, say NL of KR, find out its value and show that when r tends to 0, NL of KR is an infinite function. So this is an exercise which I am giving you, that for r tends to 0, if you take a limit of NL of KR, that is the Newman function of order L, where argument is KR, and when r tends to 0, if you calculate NL of KR, it will be an infinite function. It is having an infinity nature. So you know your wave function, whenever you solve a Schrodinger wave equation, and generally the acceptable solutions are it should be always finite, continuous and single value. Since your Newman functions are not finite function at r equal to 0, so this part we cannot take this part. So you see, This part is disappearing when you take a solution in presence of the potential. But you see, so that part is disappearing. But if you compare the solutions of the Schrodinger wave equation in presence of the potential, it is similar. But you see here that the argument part of the sine function, it is kr minus L pi by 2 plus I have a factor which I wrote delta L. This is a very important part. This we will see that is known as the phase shift. Yeah, this we want to understand. That you see when a particle is encountering, or when the particle is experiencing a potential because of the target particle, you see the radial part of the Schrodinger wave equation is consisting a phase shift term. So here let us understand what is this delta L indicates. This delta L is a phase shift, and this phase shift measures the amount by which the phase of the radial function for an angular quantum number L differs from the corresponding in the case where v equal to 0. So once again, you please remember we have solved the Schrodinger wave equation in two different regions. We have solved the Schrodinger wave equation in the region where there is no potential. So when there is no potential, the solutions of this Schrodinger wave equation is this. So it is consisting the sine term, it is consisting the cosine term also. This cosine term is because of the Newman function, and this is also the sine term is because of the asymptotic nature of the spherical Bessel function of order L. So this is because of the spherical Bessel function, and this is because of the spherical Newman functions. But when you introduce a potential, right, when a particle is very close to the scatterer, I would say, in that case, your particle is in the field of potential field. So it experiences a potential. So it will experience a force, and because of the force, there will be a phenomena of scattering takes place. And because of the scattering, you see, when you solve the radial Schrodinger wave equation, it should be similar to of this type, but your Newman function is infinite at r equal to 0 when r tends to 0. So we have the solution is of this type, a upon kr. So you see the solution is of the same type. So instead of writing a dash, here I write down al. So some constant kr. So I'm writing kr. This is sine. So this is sine. Kr minus L pi by 2 plus delta n. So this radial part of the Schrodinger equation experience a phase shift. So please remember this delta L is known as the phase shift, and the phase shifts is measuring the amount by which the phase of the radial function for angular quantum number L differs from the corresponding to the v equal to 0. Okay, that is the corresponding the case where potential was 0. So basically, the only thing is that there is a phase difference you observe here, and that is why there is a phase shift here. So this phase shift we want to understand why this phase shift occurs, what is the physics of this phase shift, which we will discuss in the next lecture. So in this particular class, we have studied the interaction of two particles via Schrodinger wave equations. We have solved the Schrodinger wave equation. We have found the radial wave function in the region which is the asymptotic behavior we have studied. We have studied at a very large distance r, and we found the solution. And we have also found the solution which is very the solutions are where your particle is in the field of a potential produced by the target particle. So here you see there are two constants which we have introduced. There is a constant A dash which we have introduced, where constant A dash is introduced where there is no potential. Potential V is equal to 0, right? And here I introduce another constant AL, where I have the case where particle experience the potential. So we have to find out the relation between these two constant A dash and AL. So the constant A dash and AR are related by a factor delta L. Delta L is the phase shift which is produced because of the potential uh, is observed by the target particle because of I'm sorry, potential is observed by the incident particle. So I'm sorry, the potential is observed by the incident particle. Incident particle experience the potential, and because it experiences the potential, because of this interaction, there occurs a phase shift in the radial part of the Schrodinger wave equation, and we will now find out the value of phase shift, and we will find out the constant AL for orbital quantum number L for the case where V is not equal to 0. So next lecture we will study uh, the solution of Schrodinger equations, and we will find out a scattering amplitude and the phase shift delta L, which is produced because of the potential produced by the target particle. I'll stop here. Thank you very much.